Very good morning. So in this session, we are going to solve the practice sheet 2, which is based on what we have learned till the lecture number 6, or you can say till the lecture number 7, part 1. Okay, so we have covered almost all the topics for the solving non-linear equations. Okay, so we have seen various type of methods for the same. Okay, so here let's go for the first problem. So first problem is evaluate square root of 5 using the equation x square minus 5 equals to 0 by applying the fixed point iteration, and you are supposed to perform at least 4 iterations. So the problem suggests you can use any fixed point iteration technique. So means you are supposed to define a scheme of the form xk plus 1 is equals to phi of xk for k equals to 0, 1, 2, 3 and so on. Right. So for getting the same, so first you need to write the following functional relation or functional iteration, or you can say in short fixed point iteration scheme in the following form. And you should make sure that this scheme should converge to the root. Okay, so there are 2 steps you need to follow. So if you look at the equation carefully, you can rewrite the equation x square minus 5 equals to 0 in the following 3 forms. Maybe more other forms are also possible. So the very first form is x equals to 5 by x. Other form is if you rearrange and you send x square minus 4 is equal to x square minus 4 is equals to 1. Okay, and then or you can say you write x square minus 5 as x square minus 1 minus 4, write minus 5 as minus 1 minus 4. Okay, then you will get the second relation, and for getting the third relation you can write at it's like minus 4 minus 1. Okay, then you arrange the things and you rewrite the equation in the following form. Okay, and so corresponding, if you the corresponding schemes are for the first case. What is the corresponding functional iteration scheme is xk plus 1 is equals to phi of xk, and for the first case it is 5 by xk. For the second part you have xk plus 1 is equals to 1 plus 4 by xk plus 1, and for the third case xk plus 1 is equals to 2 plus 1 by xk plus 2. Right. Also left hand side you are replacing x by xk plus 1, the next step, by using the previous steps. On the right side you are having, instead of x you are replacing x by xk, means you are doing input on the right side and getting output as a left side. Okay, so here you have got 3 forms. Okay, now you have to decide which one is good or which one is bad. So we know the fixed point iteration, so x square minus, if you recall the Picard-Fixed point theorem. Okay, not that if you have a function phi from I to I which maps I into I, and mod of phi dash of x is less than 1 for all x belongs to I, then phi has a fixed point, you can say S, and then the fixed point iteration scheme xk plus 1 is equals to phi of xk converges fixed point iteration scheme converges to S. So, if this is a recall of Picard-Fixed point theorem. Which is a special case of contractive mapping theorem, and you can show that if mod of phi dash of x is less than 1, so phi is differentiable, so phi is continuous. Okay, and phi is, you can say phi belongs to C2 of I, means continuously differentiable function, means its first derivative is continuous. Okay, then you have phi has a fixed point. Okay, right. So so this theorem, what it suggests us? Okay, this theorem suggests you, so suppose if the root is S, okay, if the root is S, so you are looking for the scheme. Okay, so here you can say as a remark, what you are looking for an interval I, okay, or you can say you can look a function phi such that mod of phi dash of S is less than 1, and phi certainly belongs to C2. Okay, and phi, then you can find an interval, okay, suitable interval, that S minus delta to S plus delta, that is equals to I, 2I, phi maps I into I. So these three things you require. Then this Picard's theorem gives you guarantee that the given functional relation actually converges, or it certainly gives you the root of the equation. Okay, so now if you look at here, so here S, if you see, is root 5. S is equals to root 5. If it converges, it should converge to root 5, right? So okay, and now you have to discuss for each case, okay, what will be possibly phi dash. Okay, right. So let's move to the next phase. And so if I pick up this first case, that where phi of x is 5 by x. Okay, so this is certainly continuous and differentiable except at 0. Okay, containing an interval, it will be differentiable and as many time you wish, right? Okay, so phis certainly is C2, okay, on I, okay, such that 0 does not belongs to I. So I does not contain 0. Okay, so that's very much clear. What is this interval? I is any closed interval which does not contain 0. Okay, then you are having the as many time differentiability and continuity, right? Now also phi dash of x is equals to, minus 5 by x square. Now if you wish to look at, because you are looking at the I interval near the neighborhood of root 5, so phi dash of root 5, if you try to find, is minus 5 by 5, right? Minus 5 by 5, that is equals to 1. Okay, so this implies mod of phi dash of root 5 is actually equals to 1. We certainly, you can't say less than 1. Okay, so you can't apply here the Picard fixed point theorem what you have just now see. Okay, right. So similarly you can discuss for the next case where you have taken p of x is equals to, for the second case if you look at p of x is 1 plus 4 by x plus 1, and now if you look at phi dash of x, so that is equals to minus 4 by x plus 1 whole square. Now mod of phi dash of x is equals to, okay, 4 by x plus 1 whole square, right? Now mod of phi dash of root 5 is equals to 4 by 1 plus root 5 whole square. Certainly denominator is more than 4, okay, because root 5 is more than 2 point, right? It's near about 2 point, and 2 plus 1 is 3, 3 square is 9, so near about 9, so it will be certainly less than 1. Okay, similarly for the third case, okay, similarly for the third case you can have the following. Okay, third case you have phi of x is equals to 2 plus 1 upon x plus 2. If I correctly recall, 2 plus 1 by x plus 2, right? So this will certainly apply phi dash of x is equals to minus 1 by x plus 2 whole square, and if you go for mod of phi dash of x is equals to 1 by x plus 2 whole square, this implies mod of phi dash of root 5 certainly will be less than 1. Now notice that here phi's you can differentiate as many times, but 2 does not mean, but okay, here in the third case you have phi belongs to C2 of I, any interval, okay, such where I is such that 2 does not belongs to I. I is a closed interval such that 2 does not belongs to I. Okay, 2 does not belongs to I, and then it will certainly satisfies the condition of Picard-Fixed point theorem. Okay, and of course you need to also choose an interval such that phi is from I to I. Okay, so these three things you have to mention. So first thing is very much clear, phi belongs to C2 of I, that is true, and also you can choose an interval. So you are, so I is what, so if you look at here, so root 5 minus delta to root 5 plus delta. So delta is in your control, so you choose, so root 5 is something like 2 point, right? So 2 point, so if you look at here, so you have to maintain this delta so that 2 does not belongs to I. Okay, so choose delta such that 2 does not belongs to I. So means it's sitting on the right of the 2. So it's starting the interval from the right of the 2. Okay, that is possible, right? And certainly, because see, if you are looking very near to 2, so it certainly this interval is like between some 0 to 1, and you can certainly show that phi maps I into I. Okay, so in this case you should be careful by choosing the delta such that 2 does not belongs to I, and that also can be shown that phi maps I onto I. For the second case, you are supposed to make sure one right, okay, x plus 2, right, okay, x plus 2, so minus 2 does not belongs to I, right? So we have to correct it. Minus 2 does not belongs to I. Okay, that is possible. Okay, right. In the previous case here, minus 1. So here you have to choose. Delta such that minus 1 does not belongs to I. So what is I is, if I recall, it is root 5 minus delta to root 5 by plus delta. Choose delta such that okay, so you should choose delta such that minus 1 does not belongs to I. And this first one you can reject, okay, because it does not satisfy the main condition that it is strictly less than 1. Okay, so second or third you can work, where you can go for convergence, right, which will guarantees the convergence of the resultant scheme. Okay, and then you can perform at least 4 iterations. So that is very easy. You have to just start any point inside the interval which you considered, okay, and choose a near about point, okay, from that interval, and you can perform the iteration, right. Okay, so this is about the first question. For the second question, what you have is, so consider the equation x cube minus 5x plus 1 equals to 0, and it is given that it has a root in the interval 0 to 1. So you can see that this function is a polynomial. So polynomial is continuous, okay, right, and you can see that at 0 it will give you positive 1, and at 1 it will give you negative. So f of a into f of b is negative. So Bolzano's theorem guarantees that this statement is correct. Okay, so we can write the, so what is further given is, we can write the equation in the following form: phi x, and the corresponding iteration method in the following ways. Okay, so I will discuss the first case. So here phi of x, if you look at, so it is 1 by 5 x cube plus 1. So if you look at here, it is x equals to 1 by 5 x cube plus 1. Okay, so x equals to phi of x. So phi of x is 1 by 5 x cube plus 1, and it is given that root r lies in the interval 0 1. So it is given that the root lies in the interval 0 to 1. Okay, so what we are looking, the convergence of this scheme. Okay, so for again looking for the convergence, you are going to see whether it maps everything on the, so if you consider an interval I is equals to, let's say, 0 1. So my first question is, so if this function is differentiable as many times you want, because phi is a polynomial of degree 3. So polynomial is infinitely differentiable function. Okay, now you see phi of, and moreover if you look at this function is increasing function. Okay, this function is increasing function, right, because phi dash x remain positive for any value of x, right. So if you perform the derivative test, phi dash of x is equals to, what it will be is 3 by 5 x square, which is greater than 0 for every x. So it is it remains this function is increasing over the interval 0 to 1. So you know what is the minimum value at x equals to 0, that is 1 by 5, and what will be the maximum value at x equals to 1, that is 1 plus 1, 2 by 5. Okay, so it will not go outside the interval. So it will be easy to show that phi actually maps I to I, right. So that is, so if you choose this I is equals to close 0 1, where the root lies, Okay, you can easily show that phi maps I into I. Just now you can follow by the argument that phi dash remain positive over the interval. Okay, and the that shows that it attains maximum at the left and at the right hand point and minimum at the minimum at the left hand point, and the function is continuous. So, okay, so it assumes all the values in between there. Okay, so you have this actually will not go outside 0 1. So this shows that, so this will give you guarantee that phi maps I into I. Further, phi belongs to C2 of I. Now what is remaining is, now you have to show that. So now mod of phi dash of R, I will just look at this, okay, is equals to 3R square by 5, right? This certainly less than 3 by 5, right? Because R lies inside the interval open 0 1, so R square certainly strictly less than 1, is strictly less than 3 by 5, so this is strictly less than 1, right? So all the conditions of Picard's theorem satisfied. Okay, so this gives you guarantee that this sequence, that this scheme converges. Okay, what will be the speed of the convergence, that also you can determine, because now you can see that phi dash of R is, now see, if you look at what is phi dash of R, that is equals to 3R square by 5, which is non-zero, which is not 0. Why? Because R is between open 0 1, so R is strictly greater than 0 and strictly less than 1, right? So this number will never be 0. So what it suggests you, if you refer the lectures on fixed point iteration and error analysis, okay, I hope this is a lecture 6 part 3. Okay, so this that will tells you that there is a linear convergence, you will see linear convergence. Similarly, you can discuss for the second case and third case. Okay, right. So let's move to the next problem. Okay, so let's move to the next problem now. Okay, so next problem is problem number 3. So I will be taking this first part here. So from the equation you can see that it is given that x square, the given equation is x square plus ax plus b equals to 0. Okay, and it is given that this has two real roots, alpha and beta, so roots are real numbers. Okay, then you have to show the following. So any one of them I will look at here. So I will look for first problem. Okay, so what we have from the equation is sum of the two root is minus a and product of the two root is b, that you can observe from the given equation. Further, from the first part and from the relation xk plus 1 is equals to phi of xk, you can observe that phi of x is given by the following. And certainly you can, this is a relation which you can differentiate in any interval which does not contain 0, in any closed interval which does not contain 0. So, and moreover you can see that this remains, p dash remains positive for all x in that closed interval. So you observe two things here. One, first thing is this function is, phi function is a increasing function. Whatever the interval you will consider, whatever the closed interval you will consider, it remains an increase, it is an increasing function. Okay, the next thing is, what you observe is that phi is continuously, you can differentiate as many times you wish, okay, in that interval. Okay, now for applying the Picard-Fixed point theorem, or you can say if we leave the worry regarding the condition that phi maps I into I, by noting that you can choose delta in such a way that you this alpha minus delta to alpha plus delta. If you are looking for the roots root alpha, okay, so you are considering the interval so small so that it maps. Okay, so in that case we are leaving that, okay, as an exercise that you can verify that phi maps that the interval phi maps I into I. That's easy by using these properties that phi is an increasing function, okay, and you that and also noting that 0 does not belongs to I. Okay, so by noting that you can choose delta in such a way that p maps I into I and 0 does not belongs to I. Okay, so what is required to know is whether mod of phi dash of alpha is less than 1. If we are able to show this, then we are through. Okay, so from from this relation, if you use this relation here, what it will give you is, this implies mod of b by alpha square is less than 1. This implies mod of b is what, alpha time beta, by alpha square is less than 1. Alpha will get cancelled, mod beta by mod alpha is less than 1, so this implies mod beta is less than mod alpha. So this condition satisfies only if you have mod beta is less than mod alpha. Similarly for the second case, you can look for the second case. If you look, if I wish to do one more step here for second case. So if you, for the second case, what is phi of x is minus b by x plus a. So this implies phi dash of x is equals to b by x plus a whole square. So you can look the interval which does not contain minus a. So that is here in this case minus a does not belongs to I. What is I is, you are looking that root near alpha minus delta to alpha plus delta, you have to choose in such a way that phi maps I into I. Okay, right. So what further now is, now you have to look for mod of, so now mod of phi dash of alpha is equals to mod of b divided by alpha plus a whole square, right? So that is equals to mod of b divided by, what is alpha plus a? If you look at the relation, alpha plus beta is minus a. So alpha plus a whole square is, if you look at, beta square. And what is b is alpha time beta by beta square. So beta will get cancelled. So you have mod alpha by mod beta, and which is certainly less than 1 only if mod alpha is less than mod beta, right? Similarly, you can do the problem, the last part, okay, and you can show that root converges to alpha if the following 2 times mod alpha is less than mod alpha plus beta. Okay, right. Okay, now in the next problem, you are supposed to identify the quantity to which the given method converges. To which the given method converges. So assume that the sequence converges. The generated successive approximations converges. Okay, and converges to, let's say, x. Then certainly limit of xn plus 1 is also x. Okay, and this also tells you if you take the power, it will converge to the x cube. Xn cube will converge to x cube. Xn square will converge to x square, and so on. So if you apply the limit on both sides here, if you apply the limit on both sides, what will be you are getting is you are having this relation. So apply the limit. So left side become limit n xn plus 1 becomes x, and 3 by 2 xn, 3 by 2 times limit xn becomes 3 by 2x, and xn cube converges to x cube. See, you know that xn converges to x, yn converges to y. Then xn plus yn converges to x plus y. So this is only true when both are converges. Okay, this is only true when both are converges. Okay, so once you did that, okay, once you obtain this and solve it, okay, what it will give you the following equation: x cube minus ax equals to 0, and which if you further solve, either x equals to 0 or x equals to plus minus square root of a. Now you look at this now. Now you look at phi of x. What is phi of x? Is you have 3ax minus x cube by 2a, which certainly continuously differentiable as many times you want. Okay. Also, what is phi dash of x? Is 3a minus 3x square by 2a. Now you look at phi dash of, so if you look at phi dash of 0, what is phi dash of 0? Is 3a by 2a, so that is 3 by 2, which is greater than 1. Okay. And if you look at phi dash of root a, that is 0. Okay, if you look at phi dash of root a, x square is a, so 3a minus 3a is 0, so 0 by 2a is 0. A is a non-zero number. Okay, so if you look at here carefully, so what you got is phi dash of root a is 0. And also, what is phi double dash? If you obtain phi double dash at root a, what it will be? That is equals to minus 6x by 2a. So x is 6 root a by 2a. So that is, you can say, some non-zero number. So 3 times 3 by root a, which is a non-zero number. So the convergence of the method, so this root, so this scheme will converge to the root square root of a, and the rate of convergence is 2. Okay, and what will be the asymptotic error constant is 1 by 2 factorial phi double dash of root a. If you refer the lecture, okay, the asymptotic error constant, okay, so asymptotic error constant is equals to 1 by 2 factorial phi second derivative at root a. Okay, that is going to be the answer for the last one. Okay. Now, if you look at the next problem, okay, this is the theorem on stopping criterion which has been discussed in lecture 6 part 2. Okay, so that you can look at there. Okay, problem number 6 is also solved in lecture number 6 part 3. That also you can know about Newton method error analysis by using fixed point technique. Okay, right. So let's come to the problem number 7 here. So it is asked that if R is a double zero of the function f and f is a real valued function defined on closed interval AB and it is twice continuously differentiable, then in Newton's method we have phi dash of R is equals to 1 by 2. Okay, so I will solve this now. So given f of R is 0 and f dash of R 0 because R is a double zero. Now for Newton's method, phi of x is given by the following formula. Now this implies phi dash of x you can differentiate, okay, that is equals to 1 minus, okay, f dash of x whole square. Okay, so phi dash of x times phi dash of x minus f of x times f double dash of x. So that is equals to, if you solve it, this is equals to f of x into f double dash of x divided by f dash of x whole square. Okay, divided by f double dash of x whole square. Okay, so now what we are supposed to find phi dash of R. Note that f is twice continuously differentiable function. Okay, and R is a double zero. Okay, so certainly R is a double zero means f of R is 0, f dash of R is 0, but f double dash of R is non-zero. Now f of R is 0, f dash of R is 0. So if you substitute directly R if you wish to find phi dash of R, you can't substitute directly R because it's a 0 by 0 form. Okay, so that's why you have to use limit x tends to R f times f double dash divided by f dash whole square. Now you know that if limit f of x into g of x, so if limit f of x exists and limit g of x exists, so then you can apply them separately. So what is there is, so now I note that, so if you wish to, okay, so let me, okay, so if you note that limit x tends to R, f double dash is f double dash of R. Now limit x tends to R, f divided by f dash whole square. Let's calculate this. Now it's a 0 by 0 form, so certainly you have to apply L'Hospital rule. So that is equals to limit x tends to R, f dash divided by 2 times f dash times f double dash. Now this f dash will get cancelled, and you know that the limit of this is equals to 1 by 2 times f double dash. So both limit exists. So limit of here is must be equals to f double dash of R times 1 by 2 times f double dash of R here. So this will get cancelled. So that is equals to 1 by 2. So which is non-zero? Which is non-zero. Okay, which is non-zero. Okay, so phi dash of r is non-zero now. Okay, so now again you have to go for now determine the value of alpha such that phi dash of r is 0 by redefining phi as follows. So again you have to proceed in the similar manner. Okay, and certainly you have to find phi dash of x. Okay, and so if you modify, if I wish to write few steps here, so let phi of x is equals to x minus alpha time f divided by f dash. So this certainly implies phi dash is equals to 1 minus alpha time. So you have the same thing, f dash of x whole square, f dash square minus f time f double dash Okay, so now this implies f phi dash of alpha. So this is equals to phi dash of r. I wish to find phi dash of r. So that is equals to 1 minus alpha, okay, plus alpha time f double dash divided by f dash whole square. Okay, so and you are applying limit on both sides. Okay, yeah. So if I have this here, so this implies this implies phi dash of r phi dash of r is equals to limit of this side. So what we have already obtained, 1 minus alpha plus alpha by 2. We have seen that the limit of this quantity is 1 by 2, alpha by 2, right? So and you need to equal to 0 for what value of alpha. You solve it, you will get, this implies alpha is equals to 2. Okay, right. Okay. So in the problem number 8, you have to just rewrite the secant method. You will obtain the method. So there is nothing to discuss here. For problem number 9, you have to discuss the rate of convergence for the secant and Regula-Falsi method. So that you can see the lecture number 5, part 1 and part 2. So that already has been discussed, because secant and Regula-Falsi methods are similar. Only the steps they are different. Okay, so that you can similarly you have to apply Taylor series expansion and you can solve the problem. Okay, right. Okay, so problem number 10 is here is solving the following problem. Okay, solve the following problem using secant and Regula-Falsi method at least 3 iterations. So you need to follow secant method. Okay, so for here, so if I wish to go for 1 or 2 steps here, okay, so let's say n equals to 1. So I start for n equals to 1. So x2 equals to x1 minus x0 times f of x1 divide by f of x1 minus f of x0. So what will be the value? x1 is 1 minus x1 minus x0. So 1 minus minus 1, that is 2. F of x1. So f of x1 means f at 1 value. So x equals to 1. So 3 plus 1 is 4. 4 plus 1 is 5. So 2 into 5. Divide by 5 minus f of x0. x0 is minus 1. So if you replace x by minus 1, so minus 1 x power 5, so minus 1 to the power 5 is minus 1, minus 1 to the power 3 is minus 1, so minus 1 is minus 2, plus 3 is 1. So this is what the value of x2, so that is equals to 1 minus 10 by 4. So that is equals to 1 minus 2.5. That is equals to minus 1.5. Now for n equals to 2, okay, so for n equals to 2 for the second case, okay, so you have x3 is equals to x2 minus x1 times f of x2 divide by f of x2 minus f of x1. So x2 value is minus 1.5, right? So you have x2 value is minus 1.5. Okay, so x2 value is minus 1.5, x1 value is 1, f of x1 is already obtained, that is 5, so x2 value is a minus 1.5 minus x2 is minus 1.5 minus 1 time f of x2, so f of minus 1.5 you need to obtain, okay. So what you need to get now is, so you need to substitute x equals to, so you need to find for this case f of minus 1.5. Other values are already obtained in the previous step, okay, right. Similarly you have third iteration, okay. Third iteration is n equals to 3, so that will give you x4. So x4 is x3 minus x2 times f of x3 divided by f of x3 minus f of x2. So all values x3 and f of x2 and x2 all are value carry forwarded from the previous step, and you have to new function evaluation is f of x3. So you need to, here in this step you have to evaluate f of